Dot product is very straightforward, also known as a scalar product, but the consequence of a dot product is very, very powerful. All right, because what it does is it actually helps you determine the component of one vector that's acting in the direction of another. All right, so it's a weird thing to think about, but let me just do a rough sketch for you. Get rid of the calculator because I don't think we need it for this. So if I have a vector going in, I'm just doing a classic diagram here, so let's say we have vector u and v, so this is an example. Now, the physical application of this is varied because if we're talking about movement, we're talking about force, we're talking about really anything you can think of. I mean, because a vector could be dealing with like propagation of a virus, you know, so like what are we working on here? But really what's happening is just thinking in terms of force. If you have u and v pulling on some object, they're both pulling generally in the same direction, all right? But just by, like, if I told you that u has a force of like 20 pounds, I'm still not able to fully conceptualize a Newton. I mean, I know what it's equivalent to, but it doesn't, like, in my everyday life, I don't think in terms of Newtons. Just like I don't think in terms of kilometers per hour, I think in terms of miles per hour, I can conceptualize that. You know, like everyday life is what works for me. But you know, in a physics class, in a lab, everything's kilograms or grams and things like that, meters, kilometers, and so on. And then for force, it's newtons. So if I'm saying that we're pulling 20 pounds in the direction of u and 30 pounds in the direction of v, we're not going to say that we're pulling a total of 50 pounds of force on this object here, right? Whatever that object is. Because it's pulling in not opposite directions. They're not pulling in the same direction either. They're askew from one another, right? So there will be some portion of u that's acting in the direction of v, and there will be some portion of v that's acting in the direction of u, and then the vector sum ends up being kind of the balance point where they meet in the middle. So if this object's in motion, then it's not going to follow either of these paths. It's going to follow the vector sum path. All right. So then the question would become, if I am the person pulling in the direction of v, and I wanted to have, let's say, 40 pounds of total force moving in that direction, how much force do I need to contribute? How much force does you need to contribute? I mean, because we've all been in that position where, well, maybe not all of us, but I would say, you know what? I'll say most. I would, if I had to take a guess, I would be willing to say all of us have been in this position. Maybe it's not carrying furniture up a flight of stairs, but you're carrying something, and somebody else is also carrying that same something. Maybe it's a box, maybe it's a desk or something. And in your mind, you're thinking to yourself, am I doing all the work here? Is this person actually lifting anything? Because I feel like I'm carrying a lot, and I shouldn't be carrying so much. Like, this is a 100-pound thing, and I feel like I'm carrying all 100 of that. Maybe even more, because I feel like they're like resting on it. Like, especially when it's like a couch up a flight of stairs or something like that. Like, you gonna do anything, man? You gonna be part of this? You know, so that's really what's going on in a situation like this. How much does u have to contribute? How much does v have to contribute? And what a dot product will tell us is how much u is contributing in the direction of v, all right, based on a length. So if I drop an altitude here, poor quality altitude, let me fix that. Still poor quality, but then this component, it's a vocabulary word, this is the component of u acting in the direction of v. All right, so there is a portion of u that's contributing to v. Now I could redraw the diagram so that you could see what V is contributing to U, and then you could start thinking about a balance point, whether there's equity there. Is equal parts of U going to V as V going to U? If that's the case, I mean, you're thinking about equity within a financial system. You know, like, is equal parts going in and out? You know, if that's the case, then you would want the component of U acting in the direction of V to be the same as V acting in the direction of U, right? But that's not always going to be the case. There's usually one doing the lion's share of the work. But a dot product is going to contribute to us learning about that numerical value, all right? Now, as far as the operation is concerned, it really couldn't be any easier, but it's the concept behind it that makes it important. And I've been preaching that the whole semester. Like, the math isn't bad. It's usually just multiplication and addition. And in fact, that's all this is. It's understanding what it's telling you. That's really where the real learning is happening. So U dot V is going to tell us to take, and it's going to be a scalar result, 3 multiplied by -1 plus 5 multiplied by 3 plus 2 multiplied by 0. So -3 plus 15 plus 0, because again, no matter how much you want to write it, 2 times 0 is not 2. All right, and so we get a result of 12. All right, so this is going to help us to understand the concept behind the component of a vector acting in one direction or another, because the concept of the dot product is commutative. U dot V and V dot U are going to give you the same result. So it's not like I can look at this and say, well, this is what U is contributing towards V, because I could easily turn around and say V dot U is the same thing. So are they contributing the same thing towards each other? Not necessarily. All right, but this is the building block. It's a skill that's going to help us understand where that component concept is coming from. All right, so scalar product is another name for dot product. And so it's really just asking us to do the same thing. So P dot Q is equal to 10 multiplied by -2 plus -4 multiplied by 1 plus 7 multiplied by 6. And now it's looking like 18. Yeah, so it's kind of strange when you think about it, but when you're multiplying vectors, there's two forms that you can take. One is the dot product using the dot form of multiplication, and the other is a cross product, which is the X multiplication symbol, which we're going to get to next class. It's kind of strange how the origin story behind this notation is this class, is this concept. Linear algebra is where the dot form of multiplication began historically. Right? But you'll learn early on, oh, I mean the same thing. A dot and an X, they just multiply. Yeah, I mean, if you want to oversimplify it, I guess so. But the dot product is telling you that it's okay to multiply scalars, right? Because vectors are represented as scalar multiplication. But a cross product is going to give a result of multiplication that is also a vector, all right? So the concept of the dot product is always going to yield a scalar, whereas the cross product is going to give you a vector in all cases.
So what is the 12 like, looking at it practically?
Well, that's what we're going to get to when I talk about the component, because we use that to help us determine the component of one vector and acting in another, the direction of another. So as of right now, it doesn't really mean a whole lot of anything other than to say it's an operation that can be performed between two vectors, but we're going to add in another element to it that's going to give it all the more meaning. All right. Josh, did you have one?
Oh, no, that was my
That was the one? Okay. So then you have all these operations here that you can perform, and you can see one of them is an interesting looking one. Like the first two, well, number 3 and 4, but it's still the first two. They're pretty straightforward because it's basically telling you that you can dot in either order, so that's fine. You know, it's associative or commutative property, just a little extra oomph. All right. The associative property has a little wiggle room to it, but it's number 5 really. That's the most interesting one because it's telling us that the magnitude squared is the same as the dot product between a vector and itself. And that's an interesting concept, but when you think about it, it should make perfect sense because the result of finding the magnitude is a scalar quantity. The result of dotting a vector against any other vector, whether it's itself or otherwise, is always a scalar quantity. So the fact that they'd be related in some way, that should make some kind of sense. It's just a question of, would you necessarily think that this would be the relationship? Well, that's a different story for a different day, I think. But what I am going to do is put some stars on this because you're going to verify these on your own, and we'll talk about. Okay, so we're continuing where we left off, page, I already forgot, 35. And so really it's just a matter of applying some of these nifty looking properties. Now, for number 3, it's really kind of just a matter of applying your commutative properties and associative properties and things like that. So generally it's basically saying that you can multiply in any order you want. Now when it comes to taking a dot product, it's not challenging one way or the other. So really it's just a matter of dotting. So I'll just kind of itemize it a little bit here, zoom in a smidge. A dot B is going to be 1 times 0, which is 0, plus 2 times 2, which is 4, plus negative 3 times 4, which is negative 12, so we'll get a negative 8 for that. All right, so we want A dotted against B multiplied by C. So the dot product of A and B, dot product always gives a result that's a scalar, not a vector quantity. So I'm going to use scalar multiplication to multiply negative 8 by C, and that result is going to be a vector. All right, so we're looking at negative 40, 8, and negative 40. All right, so it's just a matter of following order of operations. Like in number 4, you can dot the A against double the C value, but one of the properties above this bad boy right, let me go blue. That's not blue. Come on, blue. Tells us that we could associate a scalar multiple with any part of the product. All right, so I can dot the two vectors against each other first and then multiply it all by 2, or I can just double vector C and then dot it against A. There's basically a variety of different pathways you could follow, but since it's not difficult to just double vector C, I can just do, is that a 1? 1, 2, negative 3, dotted against double the C vector, so 10, negative 2, 10. And so we'd be looking at 10 plus negative 4 plus negative 30. And so we'd get our result once we find that sum. So it looks like negative 24. The last one I think is the most interesting one, because that, now we've kind of talked about this a little bit, That's the property of magnitude, which tells us that, and I'll show you the proof for this in a minute. It shows us that the magnitude squared is the same as the dot product of a vector in itself. So if I know vector B, I can just do a quick B dotted against B, which is going to be 0 plus 4 plus 16, result 20, and then call it a day. But let's do a proof real quick. Well, not real quick. Not quick as in I'm going to rush it. Quick as in it doesn't take long. All right, so proof of v squared is equal to v dot v in, we'll go real space dimension 3. All right. All right, so you could work on the left or the right. It doesn't make a difference either way. But I do need to establish my vector v. So let v equal v1, v2, v3. And so, you know, pick your poison, fight, you know, pick your battles, whatever your favorite cliche is, go for it. So, right-hand side, dot product's pretty easy, so why not? So I'm going to find the dot of v and v. Which is going to be v1 squared plus v2 squared plus v3 squared. All right, so that's the sum of the square values of each of the elements of the vector itself. Now, I could switch over to the right-hand side and use that to create, you know, the balance in the proof, but I don't think I need to do that because, you know, if you think about what the vector magnitude formula is, there's a radical in there. Okay, so let me just slap a radical on this. Just violated every mathematical rule in existence. You know, well, who cares, you know? I've been making stuff up as I've been going along all semester, so why would today be any different? No, if you're going to slap a radical on it, you have to account for that with an inverse operation. So I'll square it. Because the radical part is the definition of the magnitude of v squared. The magnitude of v. And by actually squaring that out, I have equivalence. All right? So I knew that in order to have a magnitude of v, I had to have this expression here, the radical with the v1 squared, v2 squared, etc. But I didn't have that, so I manufactured it. I created it. So by slapping a radical on there, I can offset that by also putting a power of 2. So this new expression is equivalent to what I started with, and as it turns out, equivalent to the left-hand side, so I have my proof. All right. Now, it's not hard to expand this out into, you know, some sort of extreme dimensional situation, you know, like 10D as opposed to 3D. You know, all you got to do is use some dots and a v sub n. You know, but I don't think that we're going to gain anything by doing that at this point. So I'll just kind of leave it at this. And besides, we're living in R3 for now, so once we graduate to higher levels of existence, higher dimensions, then we'll start getting into some more generalized proofs. Class. The last thing I'm going to do is actually show you where the formula for finding the angle between two vectors comes from. All right, and this has some trig components to it. Pretty nifty stuff. Okay, so the rule is telling us that the dot product of u and v is equivalent to the magnitudes multiplied by the cosine of theta. All right, but we're gonna take a few minutes to discover where that rule comes from, and it's gonna come from this. All right, So, I mean, all right. So it says proof, which a lot of people can't get past when they see that word. They're like, okay, so this is going to be on the test. Well, yeah, probably. But it's not a hard proof. It's just mathematical operations, so it should be okay. All right. So what we're going to do is we're going to use the law of cosines here, if you remember that. And I'll jot it down for you if you don't. So law, that is a highlighter. Law of cosines. 3 different variations, but the one people remember the most is c squared is equal to a squared plus b squared minus 2ab cosine c. That's assuming that it's represented in terms of a's, b's, and c's. But what I want to do is modify it to fit the diagram that I have here. All right, so the angle theta, I'm going to put that at vertex C. The other two are going to be A and B. Doesn't matter what's where. All right, so the C value is going to be V minus U. Now, this is vector V minus vector U, so it's vector sum, but involving a negative. But if I'm talking about just the length of the side, it's actually the magnitude of V minus U. And this would be the magnitude of V. Now, the vector has magnitude and direction, but if I just want to talk about length, all I care about is its magnitude. All right, so I'll slap those magnitude brackets on there. And we'll be looking at V minus U, magnitude, squared, is equal to U squared plus V squared minus 2 times U times V times the cosine of C. All right. Now, I'm not overly concerned with the type of multiplication symbol involved, and that's only because these are all scalars. So, oh, theta, sorry, not C. I'll change that in a sec. But these are all scalars, so ordinary computation is going to come into play. I don't have to worry about vector operations too much. All right, but let me fix this real quick. All right, so the left-hand side is the key to the whole thing. All right, because what that tells me is that we're looking at V minus U squared, the magnitude squared. We could think of it as the dot product between V minus U and V minus U. All right, so that's what I'm going to do. So I'm going to work the left-hand side for a sec. So V minus U dotted against V minus U. All right. So distribute it out. All right, so we'll get V minus U times V minus U. If I dotted that out, then I would get an equivalent relationship to V minus U magnitude squared. But by writing it this way, I think anyway, people don't always agree, but I think it's clear that there's some distributive property at work here, all right? But I can't just multiply a vector. Right? Vector V multiplied by vector V, it would not become just V squared because it's still the magnitude that I care about. So when I multiply vector v by vector v, it's going to become the magnitude of vector v squared. All right. So what we get at here is that this v minus u dotted with v minus u is the same idea as v minus u in magnitude form multiplied by v minus u. It's just one is more convenient to write than the other. This just feels awkward to write, and it doesn't necessarily feel like you can distribute it out, but if you write it in this form and then distribute it out knowing that the result has to be involving only the magnitudes, then you're in pretty good shape. Right? So then what you get when you combine it with the right-hand side, because again, we're looking to solve for theta here, we get a cancellation of, plus sign, sorry. Because two negatives multiply to give a positive. Words to live by. So the right-hand side which I guess you don't really have to write out again, but it just kind of felt naked on the right-hand side without it, so, you know, not in a creepy way, in a mathematical sense. All right, so yeah, purple's fine. So cancellation, v squared, kill him. U squared, magnitude u squared, kill him. Well, let me rewrite. The negative 2's will go away. I forgot to put the intermediate step in there. And so I'm going to have to kind of slide it in. If I distribute this out, it's v squared minus 2 dot u dot v minus u squared. And because of that, the v squared, by definition up here, becomes the magnitude of v squared, and same thing with the u squared. But these guys are going to be left, and now I'm locked in. Yeah, I got to use white out. Yeah, it's just the dot product of u and v. I got in a groove and all hell broke loose.
I'm sorry, where did the negative come from in front of the u squared?
In front of the u squared? Hold on one second. Let me clean this up and then I'll. Oh, I don't know. That I keep doing. I have no idea why. Yeah, that's just a 2 times 0 equals 2 kind of thing. I just keep doing it. Maybe that's the issue. Maybe nobody else makes that mistake except for me. And that's why I keep harping on it. All right, yeah, so sorry about that. But yeah, so the intermediate step is the one that I glossed over. I try to hand wave through it and then pay the price for it. So if you actually distribute this out, so you could think of it this way, but that's awkward. So we think of it this way, based off of the magnitude of v minus u squared is equal to the dot product of the two differences. If you FOIL this out, you get v squared minus 2uv plus u squared, ordinary algebra. All right, nothing complicated about that. But then based on one of the properties, we could say that v squared, which would be the same as v dot v is equal to the magnitude of v squared. All right? U squared, by the same reasoning, would be u dot u, which becomes the magnitude of u squared. All right? But the same won't happen on the inside. All right? And so in my desire to just put magnitudes around everything, I put it around a little too much. All right? So the u and the v, these should not have magnitudes on it because they're not consistent with any of the properties. So these two are left alone. And then once you get to this step here, the negative 2's definitely cancel out because they're scalar multiples. But you're still left with all that other stuff. But if you weren't, you'd have a problem because then you wouldn't get that rule, which is that the cosine of theta is equal to u dot v. Well, this is one of the rules, one variation of it. Magnitude of u, magnitude of v on the bottom. Or the way the rule was stated above, u dot v is equal to cosine of theta multiplied by the two magnitudes in whatever order makes sense. All right, so this is one variation of the rule, but this is the one that allows you to solve for an angle. All right, so this allows you to figure out, so it allows you to determine angle between vectors. All right, but that little blue step there, it was such an important step that obviously by my not including it the first time, the whole world came to a screeching halt. Chaos is what happened.
So allowed you to
Allows you to determine the angle between vectors.
what does that mean?
So two vectors, there's going to be an angle separating them. This computation will allow you to determine what that angle is. And so it's going to lead us to a concept called orthogonality, which is basically determining whether two angles are separated by 90 degrees, or two vectors are separated by 90 degrees. So let me just take you through an example, and then I'll star another one, and then we'll be done with the lesson for tonight. So the first one's in IJK notation. So I want to dot these two vectors. So I'm going to write it in component form. Column vector notation 1, 1, 1. Dotted against 2, negative 1, negative 3. So I didn't designate one as vector u and the other as vector v, but there's no reason why you can't. So we can call the first one u and the second one v, just to keep it consistent with the formula. All right, so 2 plus negative 1 plus negative 3. We're talking negative 2. All right, so u dot v would be equal to negative 2. All right, so now what I need is the magnitudes. So since I'm calling the first one vector u, this is something that you would not need to show work for, because I'm not going to take the time to show you a program and then tell you you can't use it. Not even show you a program, show you how to write the program and then tell you you can't use it. All right, so when I'm looking for the magnitude, I'm just popping it in. Now, again, it's not a hard computation to do by hand or in your head, but I don't want to do it. So radical 3. And besides, to get the angle, we're going to have to do it in the calculator anyway. All right, so vector v, 2, negative 1, negative 3. So root 14. All right. If at any point you didn't get your program to work, definitely take a look at the video that I posted. And then if you still can't get it to work, then talk to me, because you can see we've already used it like 7 or 8 times already. Now, it's not a big deal. Again, you can do it by hand, but I'm cranking these babies out like nothing. maybe it takes you another 15 seconds for each one. It starts to add up. Was that 105 seconds? That's like an eternity. All right, so cosine of theta would be equal to the dot product, which is -2, over the product of the magnitudes u and v, which would be the square root of 42. Just doing the quick mental math. Ideally correctly. It's always a plan. And so theta is going to be the inverse cosine of -2 over root 42. So we're talking about approximately 108 degrees. I'm just going to check, make sure nobody messed around with my mode. Nobody did. So about 108 degrees, roughly, if I'm rounding to the nearest degree. So, you know, it's not a right angle between them, but it's not too far away from being a right angle. Now, thinking back to the unit circle, can you think of instances in which the cosine of an angle, I'm sorry, let me just ask this a little bit more clearly. 90 degrees, that's orthogonal or perpendicular, all right? What's the cosine of 90? 0. Okay, so if there is going to be an orthogonal relationship, then the whole right-hand side would have to zero out, right? In order for a fraction to become 0, which part of the fraction needs to be 0? The numerator. So what that's telling me is that the dot product of u and v is equal to 0, then you're looking at an orthogonal relationship, all right? And that's based on it's not a fact as much as it is unit circle trigonometry, which is something that people often lose sight of, but I tend not to let people do that, all right? So this relationship is really just telling us that if you can find the dot product between the two vectors and it turns out to be 0, then you, without doing any other work, you already know that it's an orthogonal relationship. And there's a lot of stuff that we're going to do with that piece of information. So developing fluency with it is important, but we've already learned repeatedly that the vocabulary is important. So moving forward, I guess let's start off with just knowing that orthogonal means that it's talking about a right angle between two vectors. All right, not just vectors, but we've got to start somewhere. All right, so that's an important piece to keep in mind, because we call it perpendicular in two-dimensional space, but in three-dimensional space, it's not just like this. Could be like this, could be like this, it could be in any orientation that makes a right angle. As long as there's a right angle between two vectors, you're looking at an orthogonal relationship. And I'll tell you, it's infinitely more difficult as you increase the degree of space. So 3D, 4D, whatever, it gets harder and harder to visually determine if something is a right angle. Because I'll tell you right now, if I asked you, my two fingers forming a right angle, you look at it and say, your guess is as good as mine. You haven't showed us from the right perspective. Now, if I tell you, if I turn my hand, you're like, still hard to tell, but I'm thinking probably not. You know, but at least you have a fighting chance of making that determination. So then the question becomes, once you get into four space, how do you, because you're not looking at the picture, how do you determine that kind of relationship? All right, and that's where we're moving towards. All right. All right. So on the next page, we had to find the measure of the angle between vectors. So we did the one problem, but I left another problem for you to do. So we're going to call the first vector again u, and the second one v. Essentially, if we're going to do all this work, in order to find the angle, we need really three things, three unique things. One would be the dot product of u and v. Another would be the magnitude of u and the magnitude of v. That's for any situation. But as it turns out in this case, 2 times -2 is -4, plus -20, plus 24. You have a dot product equal to 0, all right? Which is actually going to make these two values irrelevant. Oh no. As long as neither u or v, u nor v, I guess. I don't know. Feels wrong to say that. Like the one time I'm concerned about grammar. I don't even know if I'm using it right. As long as neither u nor v are the 0 vector. All right. And that's because of our formula. All right, we have cosine cosine theta is equal to u dot v over a bunch of other things, but cosine of theta is going to be equal to 0 no matter what the bottom is, as long as you're not dealing with the 0 vector. And the reality is, what kind of angle are we talking about if there is a 0 vector? Because I could just draw a quick sketch. Here's 3 dimensions. Let's say I have a vector going off in this direction. It doesn't matter. I'll call this u. And then I have vector v as the 0 vector. So that would be v there. I don't even want to draw the line. I'll just draw the v. Like, what angle would exist? There's no angle separating vector v and vector u, so it would be completely irrelevant. All right. So, but it wouldn't bear out in the formula anyway, because you get 0 over 0, which is indeterminate. All right. How do you find the inverse cosine of something that's indeterminate? Cosine is a function that's continuous everywhere. So expecting something to be indeterminate or undefined or imaginary wouldn't make sense. All right. But from this, we get the idea that, you pop it in your calculator if you want, but general knowledge of the unit circle, it's funny how that keeps coming up, tells us that theta would have to be 90 degrees or 270 degrees. All right, so I only paid $24 for this thing because I don't want to spend $100 for the Apple Pencil. But now I'm dealing with, sometimes it doesn't want to write. So maybe I shouldn't have been such a cheapskate. But then again, it requires spending more money.
It is a tax write-off.
It is. Pause. And record. Right? So I have the IRS knocking down my door because of the video I post on YouTube. The one time somebody watches a video. It's like, thumbs up, by the way, you have a summons. So anyway, 90 degrees or 270 degrees technically, but really if you're thinking about a vector that's separated by 90 degrees from another vector, then it's inherently separated also by 270 degrees. All right, so I'll just draw it in 2D, for example, just a quick example. So let's say you have the vector, just very simple, vector I and vector -j. See, and I'm going to try to write a j for the next 20 minutes or so. I almost bailed on dotting the j there. All right, so we could be looking at maybe the -j vector, which is 270 degrees. Or it's possible that we could be looking at I being separated from just the j vector, in which case we're looking at just 90 degrees. All right. So it is entirely possible that it could be one as opposed to the other, but you do have the benefit of having the vectors available. So you could actually just plot them and see what that relationship is. But what you do know is that they are separated by a total of 90 degrees in some capacity. All right, you could even look at the I and negative j's also being separated by 90 degrees. It's just 90 degrees in the clockwise direction as opposed to counterclockwise. Bottom line is, you know that there's a right angle involved. When there is a right angle involved, we call it orthogonal. All right? So that's the case, and this is the discovery component. We just really established that if the dot product between two vectors is equal to 0, then those two vectors are themselves orthogonal to one another. Right? So it's just a matter of, in a lot of cases, ignoring everything else. As long as you're not dealing with the 0 vector in any way, shape, or form, all you have to do is dot the two vectors and see what you get. So 1 times 10 plus 0 times 3 plus 5 times negative 2. So do all that work and you get 0. Therefore, A and B are orthogonal. All right, so we didn't have to do all that work to make that determination. It's when we don't know what's going on and they're not asking us anything about orthogonality. You have to find the angle, then it's a different story. But, I mean, as questions go, that one is not bad at all. So this was teased in the last class when we talked about the tech assignment. So now we're going to get into like the underlying structure behind all those things that you're asked to do in the tech assignment related to lines and planes. All right, so yeah, the moment you've all been waiting for. So the objective, I think the objective is pretty straightforward. But what we do want to do...
You want 2 cold slices?
I'll take 1 cold slice. Well, I'm trying to do what I can. What we have to do is come up with parametric equations to represent the line in 3 space. Because, and actually this I could do on GeoGebra. So to find the parametric equation for a line L that contains a given point, x sub o, y sub o, z sub o, that is parallel to the given vector ABC, use the fact that the displacement vector between the given point, p sub o, and any arbitrary point on the line must be parallel to v. That's a lot. Let me draw a diagram. You know how for linear functions in 2 dimensions, all you needed were 2 points on a ruler to create the line? It's the same idea here, except it's just harder to draw the line, but it's still doable. What we need are our 2 points. One of them, you can put it anywhere you want. I'll put it over here. P sub o, which is x sub o, y sub o, z sub o. And when we say the subscripts of 0, or O as I say it, poor quality subscript, let me just fix that. We're talking about particular values, all right? Now I want a variable quantity, x, y, z. That's going to be defined in terms of those values. Now, the displacement vector between P sub O and P, so I can just highlight that. This guy right here needs to be parallel to that vector v in order to define the equation of a line. All right, so what I'm going to do is find the displacement between p sub o and p, vector p sub o and p, which is going to be x minus x sub o, y minus y sub o, z minus z sub o. If you're looking for a displacement vector between 2 points, all you're doing is subtracting the corresponding parts. All right, that multiplied by some scalar should give you v, or the other way around. All right, so we could say it as, really, it really doesn't make a difference. You can go one way or the other. So I could say that POP, so the vector POP, we can say that multiplied by some, we'll use a scalar t, that's just because how the parametrics are defined. They're usually defined in terms of time, so we go with a t, but normally if I had a choice in the matter, I would define my scalar multiple as a k value or a c value. C is already taken. The k value is the preferred one, but if t is going to be in any parametric equation anyway, then why not just use it right from the get-go? All right, so I can look at this as POP is equal to t multiplied by v. All right, so that would be the scalar product of t and v. And what I get from that is x minus x sub o, y minus y sub o, z minus z sub o is equal to t multiplied by ABC. Because the only thing that, when you're dealing with parallel vectors, the only thing that makes one differ from the other is a scalar multiple. All right. Two vectors are identical if the scalar multiple is 1. All right. Vectors are going in the opposite direction if the scalar multiple is -1. All right. One vector is twice the length of another if the scalar multiple is 2. All right. So if these are going to be parallel vectors, they're just going to differ by some scalar multiple. And so now what I can do is actually define these equations by saying that x minus x sub o is going to be equal to t times a. All right. Same idea for the y minus y sub o. It's going to be t times b. And then z minus z sub o is going to be t times c. And just by adding your initial values to both sides, you get the parametric form. All right. So that's a nice little formula derivation. Just invented some rules for three-dimensional space, and this is really where where that stuff from the Bezier curves and things like that are coming from. It's just those are not just limited to linear functions; they're dealing with curved functions. But it's the same idea. If you're going to represent a path in space that's not related to a plane or a full surface, then you have to do it parametrically. So a parabola, just a parabola, you couldn't type in y equals x squared because that's going to be for all z. All right, so you're going to have a parabola with infinite depth. All right, so you would define it parametrically. The vector form of a linear equation is actually fairly simple because we're dealing with x, y, z. And what x, y, z is equivalent to, in this case, x sub o plus ta, y sub o plus tb, and z sub o plus tc. All dependent on what your parallel vector is. So you need a point, but you also absolutely, I mean, you're not going to get anywhere without identifying what the parallel vector is. So, how do we do that if we're dealing with real numerical problems? Well, one of the 2 points is going to be your start, and the other is going to be your stop. Now, in 3 space, it doesn't matter which is which, because, you know, in 2-dimensional graphs, you read it from left to right. In 3-dimensional space, what's left and what's right? You know, because you're talking x-axis and y-axis, and then right up is the z-axis. I mean, some might say left is towards the negative x-axis. So other people might say it's towards the negative y-axis, so it's a matter of perspective. It really doesn't matter, in the absence of context, it really doesn't matter what you define as the earlier value, all right? Because it could go in any direction, it's omnidirectional. So what I'm going to do is figure out what ABC is, because I already know what x sub o, let me do that in a different color, x sub o, y sub o, z sub o is. That it could have been either of the 2 coordinates. Maybe you want to use the other one because there's a 0 there. That's fine, all right? But it really doesn't matter. The ABC, so the vector v if you want, but it's really the ABC values that are in the parametric form. It's going to be the displacement vector, which is the difference between the 2 coordinates, all right, with corresponding parts. So we're looking at 1 minus negative 3. Or negative 3 minus 1, it doesn't make a difference. I'll do negative 3 minus 1. Just keep it consistent with like all the math that you've learned throughout your lives. Usually take the second value and subtract from it the first one. So we're talking negative 4, 1, and 2. So we could define x, y, z a couple of different ways. Since we know what a, b, and c are now, we could say that this is 1 plus, or sorry, 1 minus 4t. And we could say 4 plus 1t, or 4 plus t. And then the z value, the z sub o, is negative 2, so negative 2 plus 2t. All right, so that's one way to do it. Now it's the vector form. You could also write it in parametric form. Or we could say 1, 4, negative 2. That's our start. Use your variable as a scalar multiple, so plus t times negative 4, 1, 2. That, in a lot of ways, is a lot nicer. Just because, well, a couple of reasons. One, we're not really doing too much other than reorganizing stuff that we already have. So you have your start value, that becomes the vector. And then from there, you have the multiplier associated with your parallel vector. All right, that's fine. But also, I think more importantly, it ties together with stuff that we were doing in the last unit. All right, and so when that happens, that's generally not a terrible thing. All right, but, you know, I leave it up to you which way you want to represent it.
So the x, y, and z, you don't have to write it in the section.
This x, y, z?
Yeah.
Oh, I mean, if you were writing your final answer on a test and you just wrote this, that would be a problem. I didn't write it there because I wrote it here. Okay, so it's got to be there somewhere. All right, so again, you could streamline the process a little bit because really it just comes down to figuring out what your ABC values are, which is the displacement vector between P and Q in this case. Capital Q, not lower. So 3 minus 2. Negative 1 minus 1, and 3 minus 4. All right, so we're looking at 1, negative 2, negative 1, Now that's vector PQ, but that's the displacement vector, which means that this is the same as saying that we now have our ABC values. All right, choose one of the 2 points as your x sub o, y sub o, z sub o, and then pretty much go from there. All right, so I can do one of the 2 varieties. I could say x, y, z. Is equal to, put it all in linear form. So I would be saying my start point, 2, and then plus 1 t, so 2 plus t, 1 minus 2t, and 4 minus t. So that's the vector way of writing it. Or I can parameterize it and write it as 2, 1, 4. The benefit, again, of writing it this way is that you could just snag your initial point and make that a column vector plus your parameter t multiplied by your ABC, which is 1, negative 2, negative 1. Now, you might find this kind of surprising, but we've actually kind of already learned this, even the part where we're coming up with the equation of lines. So back in the last unit, when we would say something like vector 1, 0, 1 plus x4 times vector 2, 1, 3, that was a linear equation representing the intersection between 2 planes. It's just we hadn't learned what a plane looked like, we hadn't learned any of the characteristics of planes, and we were just learning the algebra kind of in a vacuum. You know, they were just saying, okay, here's an operation. How do you solve this linear system? What is it going to give you? But in reality, it was giving you this. It's just we wouldn't use t, we would use x sub 4, because x sub 4 was the free variable. Here, the t is the free variable. We can define our solution to the intersection between 2 planes, for example, as a linear equation.
So can t be any value, or
T can take on any value, yeah. Because we don't have any restrictions on what the length of the line would be. So if we did, then that would be a different story.
Would it be wrong to say 3 plus t, negative 1 minus 2t, 3 minus t? Or is p our initial?
P is our, once you do your displacement vector, that P becomes your initial. If you did it as 4 minus 3, 1 minus negative 1, and 2 minus 3, then that would make your Q the initial. So
Okay.
perspective is important.
So, sorry, that's not like the actual line itself, it's just pointing towards the line that the 2 planes intersect at.
No, this is an actual equation of a line.
Is an actual equation of a line.
Yeah. So just like y equals 2x is the equation of a line depending on what x is,
Right.
that'll put you in a different position on the line. Since we have infinite possibilities for t, this would create a line that goes off infinitely. It's just a question of where you are on that line or what piece
It
you're
would
interested
create
in.
that line though, like it's not like the actual line like going from the origin.
Oh, no, not from the origin, because it's only parallel to that vector through the origin,
Gotcha.
or starting at the origin.
Can you say that again about perspective, in terms of choosing what your starting point's going to be?
So once you're looking for the displacement vector, here I made the choice to take my q values and subtract from it the p values. So that pins p at the origin and makes that my initial value. Right? If I did it the other way around, if I subtracted the p values from q, I said that right? The q values from p is what I meant to say. Then that would change the perspective. So basically it would be, instead of 3 minus 2, it would be 2 minus 3, and then 4 minus 3. That makes our initial value q. And so when I'm writing my vector equation, I would have my start value be 3, negative 1, 3. All right, so the next couple of problems that I would normally throw a star on this and leave it for you to do, but the number 5 is a really important question that talks about where you would have intersection of two lines in 3 space. And so we can't do that without doing these. So I'm just going to take you through. We're just going to write the solutions of these fairly quickly so that we can get on to number 5. All right. But number 3 is actually, I mean, it's not bad at all because they gave you the x sub o, y sub o, and z sub o. So this is our x sub o, y sub o, and z sub o. And this is our ABC. All right, so if I want to write my equation of a line, it's going to be x, y, z. Is equal to, I'll write it in vector form, 3 minus t, 1 plus 6t, and 4 minus 3t. All right. Now, for the other one, I have to find the displacement vector first, but that's, as we're seeing, it's not the math that makes that challenging. It's just a question of getting your perspective down correctly. So when I'm looking for my ABC, I just want to make sure that whatever is coming second in the subtraction, that's going to be my starting point. So if you're consistent with it, then you're always going to essentially make the first coordinate your x sub o, y sub o, z sub o, because I'm going to do 5 minus 1, negative 2 minus 1, and 7 minus 2. So I'll have my parallel vector at 4, negative 3, 5. All right. So I could write this equation as x, y, z. And we'd be looking at 1 plus 4t, 1 minus 3t, and 2 plus 5t. All right. So then is when we get to the interesting part. And you may look at this as finally the part that connects it to linear algebra. Fun fact, it's all linear algebra. They're lines, so it must be. No, it's when you think of the linear algebra, so far you've been kind of trained to think in terms of matrices and things like that, but we have column vectors all over the place. It's just a question of, will we get back to using matrices to kind of do the work for us? Because we kind of liked when that was happening. Not the ones where you had to do the row reductions by hand, but the ones where you just type it in your calculator and hit RF and hit enter and just write down the answer and say, oh, it's independent, or oh, it's a trivial solution. And we like those problems, so we can get back to that a little bit here. But the setup is going to be the important piece. So we have to determine whether the previous two lines intersect. So got a little bit of an issue, and I'll kind of talk you through. Well, I'm going to show you 2 different ways to attack this problem, and then I'll show you why one is the more appropriate solution than the other. So one way to do it would be in terms of location. All right. So what if 2 lines are going to intersect, they have to share a common coordinate, right? So one thing that you could do is set your equations equal. So we'd be looking at, and I'll write them without the x, y, z because I don't think we need that now, 3 minus t, 1 plus 6t, and 4 minus 3t. All right, so that's my first equation. Second one would be 1 plus 4t, 1 minus 3t, and 2 plus 5t. All right, so if I'm going to tackle it this way, I would set some corresponding parts equal to one another. So I would say 3 minus t is equal to 1 plus 4t, and then solve from there. All right. Now this is going to lead us to a conclusion, but it might not be the kind of conclusion that we're expecting. All right. So I'm going to subtract the 1, I'm going to add the t. So we're looking at 2 is equal to, what is that, 5t. So t is equal to 2/5. So what this is saying is that we'll have equality between these two vectors if t is equal to 2/5. All right, so then what I would do is I would test that out for the other components to the vectors. All right, so I need to know, is 1 plus 6 times 2/5 going to be the same as 1 minus 3 times 2/5? Because if it's not true, then we're saying that we can't get equality here, because that t has to be true for each component. All right, so 1 plus 12/5, so it's 17/5. And then 1 minus 6/5, that's negative 1/5, so that's definitely not true. So the question would be, can we safely conclude that these two lines are not going to intersect? Well, first off, let's kick over to GeoGebra and see if they do in fact intersect, and then I'll show you the other approach. And then I'll show you, or explain to you, hopefully in a way that makes sense, why one means one thing and the other means another thing. All right, so here's the important ingredient. Systems are defined based on their own variables. So this t generally represents time, but it doesn't have to represent time. But let's say it did represent time. Who's to say that time is working in the same units for this system as it is for this system? We don't know that for a fact. All right, maybe time is in hours here, maybe it's in days here. That's a piece of information that we don't know. We don't know that we're dealing with a consistent set of units. All right, this assumes that the units are identical. All right, and so what this is telling me is that if time is flowing at the same rate, because the units are the same, then there would be no instance in which the paths would cross. I kind of look at it with parametrics, it's always a road in my mind. The path is the road. The points, they get plotted based on the value of t. They're like how you define t. The points plotted is you moving along the road, or are you moving along the road? Grammar is no good. But like how you move along the road is the definition of a parametric model. Because, I mean, if I wanted to graph a parabola in 2 dimensions, it would just be y equals x squared. So why would I need to write x equals t, y equals t squared to represent a parabola? Because I want to establish a component of time. All right? It's the same idea here. It's just I have to ensure that I'm allowing for flexibility in the different units from one system to another. All right? So this assumes consistent units. All right, so let's not make that assumption. Let's redefine our system. 3 minus t, 1 plus 6t, 4 minus 3t, And instead of writing the second one with t's, choose a different variable. R. I mean, you can use whatever you want, just as long as you're allowing for them to represent different quantities.
1 plus 12.
Oh, thank you. All right. So if we do that, we're going to get the intersection, because now it doesn't matter whether or not the points as the graphs are being plotted. It doesn't matter if they get to that intersection at the same time. It just matters whether or not the paths cross. So really, when you're talking about the system that we solved, you're actually trying to determine by solving that whether or not there's a collision. So you got two roads that are intersecting. That system that we solved is determining whether the cars driving on those two roads will collide at the intersection. What we're doing here is determining whether there's an intersection at all. All right. So will the roads cross? All right. That's not dangerous at all. That happens all the time. All right. Whether or not two cars are crossing the intersection at the same time, that's a different story. You know, like that intersection over there. People still don't get, I mean, there's no stop sign on the way in. Like, I think I'm more angry at the people who stop without the stop sign being there than I am at the people who are waiting patiently, and then they're like, well, I'm not going to wait here until midnight, so I gotta jump it at some point. But like the people who come to a stop, I mean, make your intentions clear. Like, just go. So I'm like blaring the horn at them. Anyway, but you know what? That's still not as bad from a student standpoint as a person tailgating another person on the way into campus, and then later on finding out that it was their teacher they were tailgating. That's always good. You know who you are. No, I'm just kidding. It didn't happen in here. But it did happen one semester, and I had to tell a student, I'm like, you do that again, I'm going to fail you. I don't even care what your grade is. I'll explain to them later. Oops, I made a mistake. I accidentally put him down for an F. I'd be like, okay, well, you're going to fix that, right? Yep, I'll get around to it. And then I won't get around to it. So, yeah. Just be respectful on the road, that's all. All right, so we have 3 equations with 2 variables. So we're going to get a solution out of this. It may be one of those infinite solutions, you know, a dependent situation, but we'll get something. So let me just move some things around. I'm going to bring the r's over to the left and constants over to the right. So we're looking at negative 4r minus t is equal to negative 2. 3r plus 6t is equal to 0. Negative 5r minus 3t is equal to negative 2. All right, so we got a system here. Negative 4, 3, negative 5, negative 1, 6, negative 3, negative 2, 0, negative 2. We're going to RF this bad boy and see what we get. Yeah. Matrix A, 3 by 4. Oh, that's not what I want. Come on, get in there. Son of a gun. Oh, 3 by 3. So negative 4, negative 1, negative 2, 3, 6, 0, negative 5, negative 3, negative 2. Bless you. Double check a Ruski here. Looks good. math, ref this, oh, sorry, second matrix, ref this bad boy. Matrix A. And we get that, oh, look at that, that's lovely. All right, so math frac that. Whole lot nicer. All right, in fact, I don't even think I need to copy paste that, I could just write it out. So 1, 0, 4/7, 0, 1, -2/7, and 0, 0, 0. All right, so
What do you click to get fractions?
oh, math, enter, math, frac, and then enter again, and it converts it over for you. That was that life-changing technique I went over. So what we're getting here, after all of this, because we have one row that's completely irrelevant, because we don't have a third variable. So we're getting from this is that R is equal to 4/7, and T is equal to -2/7. All right, so you can kind of look at it as, I mean, if T represents time and R represents, well, they both represent time in some capacity, maybe different units or different moments throughout the day or something like that. It's just basically saying, yeah, there's going to be an intersection. It's just a question of when it's going to happen, you know. So I can plug the R value into this vector and then the T value into that vector. So one way to handle that, I mean, it's entirely up to you if you want to do this, but you could take -2/7 and store it in as, I mean, you want to use T, so alpha T, I mean, it's different on yours, mine looks just awesome. All right, so, and then 4/7 stored in as R. Actually brings up a QWERTY pad. I mean, now I'm just showing off. It's crazy. So 3 minus T. Of course, I got to hit T every time now, but you know. 1 plus, oh, and then math bracket. So you could get the computations that way. It's not, I wouldn't call it quick and easy, but it's not terrible either. The quicker, easier way to do it would be to use the squiggly brackets and then actually type in everything. So 3 minus T, comma, 1 plus 6T, comma, 4 minus 3T. Close up your squiggles and hit enter. It'll substitute all those values in for you and then do the math frac just once. All right, so this gives us the coordinates of intersection of, well, it's actually a vector, but it's a vector terminating at these coordinates. So it would be intersect at coordinates 23/7, -5/7, and 34/7. All right, so they would have a common vector at that location. Now, you might want to verify it and make sure that you didn't just botch that, because, you know, that's something that I'm pretty good at doing. So 1 plus 4R, comma, 1 minus 3R, comma, 2 plus 5R. Close your squiggles. You get that, which you could see is the same decimal as the one above, but just for giggles, I'm going to math frac, and you see I get the same values. All right, so they're giving us the same ordered triple, but it's just taking different parameters for each different vector to get them there. All right. So it's kind of like two cars. I always go back to the cars. Two cars driving driving down a road. One's a little smart car, or a little like a Prius, or like a little car. I don't want to offend everybody's cars, but like the little ones, the ones that, like, if you get into a car accident, you die. All right, those kind of cars. And then the other one is like a big muscle car, like you barely step on the gas and you're going 100 miles an hour. All right, they're going to get to that intersection at two different times, just based on the nature of the variable's type of car. All right, and so yeah, they'll both get there. It's just the circumstances under which one gets there is going to be different from car to car. All right. Yeah. Question.
Is there a negative also for this?
There is not supposed to be.
It's dirty.
Is this screen?
Oh yeah, there's schmutz on the screen. Yeah. All right, and so now I think personally, give you a variety of different instances in which you could create the graph of a plane, but I didn't give you really any structure to it. I was like, well, what if I type this in? What if I type that in? But I never showed you, like, well, what if your plane has to have certain characteristics? If that's the case, you can't just say, well, what if I type in a 2x plus 3y equals z? Like, it doesn't work that way. All right? Now, what we need to have is a starting point, just like it was the case with the linear equations, but we also have to have a normal vector. All right? So, N for normal. But normal and perpendicular are synonymous. All right? So I need to find the vector that is normal to the plane itself. And then we use that to define the plane. All right? Sounds complicated, but it's actually not really complicated at all. It's the kind of thing I would say that you're probably going to end up looking forward to doing, dare I say. So we have the normal vector ABC. We're going to be dotting that against our displacement vector, which is the same kind of displacement vector from linear equations. All right, the perpendicular part is the important piece. All right, because perpendicular and orthogonal, they mean the same thing. All right, so orthogonal is the case where the dot product between two vectors is equal to 0. So all this is telling me to do is find the dot product between these two vectors. All right, so I'm going to dot A against x minus x sub o plus B multiplied by y minus y sub o plus C times z minus z sub o, and the result will be equal to 0. I can distribute ax minus ax sub o plus by minus by sub o plus cz minus cz sub o is equal to 0. Now, big old mess, but within this big old mess is the ABC part, which is the normal vector. And so, notation. I got my Calc 3 notation in here if somebody wants that. Although my phone just buzzed like 45 seconds ago, so maybe somebody already submitted it. But we'll see. Yeah, that should be the column vector notation. Keep using, I get my wires crossed. I mean, I guess as long as I don't forget what class I'm teaching. I've had some teachers do that when I was a student. That was great. I had a teacher forget that we had a final exam. That would have been great, except I also forgot we had a final exam. So I showed up, instead of at 10 a.m., I showed up at 1 p.m., wondering where everybody was. Saw some people walking around, and was like, where is everybody? They said, oh, well, the professor forgot about the final exam, and then eventually remembered when somebody went to the office, so he didn't remember. Somebody was like, you have a final exam. So he let us take it as a class, like a class final exam. Like he just gave it to them and said, okay, just bring it to my office when you're done. It's like, oh, that would have been great. Except I wasn't there for that. So I had to take the exam all by myself. Hyperbolic geometry. It sounds hard, because it was hard. I did all right, but it would have been so much easier if I could have just like, hey, what'd you get for numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? So, yeah, I guess as long as I don't forget to show up and give a final exam, I guess everything will be okay. Now, all this stuff is going to be some constant. Because you're multiplying the scalar values together, all right? It's going to be some kind of result. So what they do, those textbook writers, they say, well, we don't really need to know that piece of information in all cases, so we're just going to call that D, just to have a more concise formula where D is equal to the dot product of ABC and X sub O, Y sub O, Z sub O. Because really, I mean, anytime you have the sum of scalar values multiplied, you're talking about a dot product. It's just a question of what form it's in. So A, X sub O, B, Y sub O, C, Z sub O, that's all, it's all saying dot product. All right, when you talk about linear combinations are a result of a dot product. All right, a scalar dotted against a vector. All right, so, or a set of scalars dotted against a vector. So really, this tells me that it's very easy to write the equation of a plane if I know the normal vector and I'm capable of finding a dot product. All right. Well, let's see just how easy it is. Find the equation of a plane containing the point. Okay, so that's my X sub O, Y sub O, Z sub O. And the vector three, 3, 6. All right, so first I'm going to take the dot, because that's the harder part. And by hard, I mean like the part where you actually have to do something. So D is equal to 3, 3, 6 dotted against 2, 2, 1. So 6 plus 6 plus 6, so a total of 18. So my plane equation is the ABC values dotted against X, Y, Z. So really it's just ABC written as coefficients for X, Y, Z. You're looking at 3X plus 3Y plus 6Z, result is 18. And that's the equation of the plane. Now, I often kick over to GeoGebra to show you what that would look like, but I don't think you need GeoGebra to see what a plane looks like. I gave you a bunch of examples already. What we do need to figure out how to do is actually come up with a rough sketch of that plane. And so the way we handle that is we graph it by intercepts. All right, so what we're going to do is we're going to figure out the x-intercept, y-intercept, and the z-intercept. All right. X-intercepts you get by subbing in 0 for the other dimensions, y and z. So it's just 3x equals 18. So x is 6. Oh, that's the y. The y-intercept, replace x and z with 0, and you get 3y is equal to 18. So y equals 6. And the z-intercept you get by replacing x and y with 0, and we get 6z is equal to 18, which means that z is equal to 3. All right, now, if you tried to come up with a two-dimensional rendering of a plane, basically you'd be shading in your entire piece of paper because it's infinite. And it doesn't matter what angle it would be on, it would all look the same. All right, so the way we handle it is by drawing a straight line segments from point to point along your axes. Best you can, and then just shade it in. It's not going to be infinite. Really what we're getting is the axis cross-section of, or axes cross-sections of the plane. So where it would be in that corner. So it's like, I know, because again, when I first talked about 3D, I used these bounds as my x, y, and z axes. Basically, it's saying that I got a piece of plywood that would be leaning against the wall. But if it's a real plane, it would go through the floor and through the wall, through the roof, etc. What we're doing is we're cutting that piece of plywood to fit the natural boundaries of the actual room. So it would be triangular in shape in order to fit, assuming that this was actually a wall. It would have to be triangular in shape in order to fit these restrictions. All right? So that's really all it's coming down to, because we got to do something, and that's really the best we can. All right. So number 7 is really just asking us if you're given a point and you know it's going to be parallel to another plane, then the normal vectors, and this is something that if you had a chance to really get into the tech assignment, you've kind of learned this already. If not, I'm kind of giving you one of the answers to a question on the tech assignment. So the normal vector, in this case, wrong course, is equal to 2, 1, 1. Parallel planes have parallel normal vectors. All right. So basically, I know the ABC value for this new plane. All right. So the new plane is going to have a normal vector ABC also equal to 2, 1, 1. Now, if it were to say that this new plane had to be orthogonal to the original plane, then I would need to come up with a normal vector that when dotted with the original vector would give a result of 0. That's a little bit more complicated. Doable, but more complicated. And I know I'm going through this point, x sub O, y sub O, z sub O of 3, 1, 4. All right. So I'm going to dot, just like I did up here, I'm going to dot my normal vector against the coordinate. Doesn't matter what order you do it in. So ABC dotted against x sub o, y sub o, z sub o. We're looking at 6 plus 1 plus 4, so we're going to get an 11. So we're talking for a final answer here, 2x plus y plus z is equal to 11. All right, so RF, matrix A, and we get that. Oh, look at that. Math, enter, or math option 1, enter, however you like it. And we get that. I mean, as long as math frac continues to be a thing, this will not be intimidating because I don't have to worry about writing all this out, all right, all that decimal stuff. And then, you know, like let's say math frac didn't exist. You'd be on the hook for the exact value. So if the calculator was only going to give you a decimal approximation, you'd have to scrap it and go right back to the row reduction techniques. Which honestly, first time I taught this course, I didn't know that that MathFract worked on matrices. So I told them, if you get a decimal, you gotta scrap it and go back and do it by hand. So even I'm capable of learning a thing or two along the way. Even I, like I'm some sort of special person. Yeah, the day I stop learning stuff that's new is the day I'm just gonna call it all quits. Just retire from life. Just become a hermit and just maybe live in my mom's attic or something. You know, just go back home and just live up there with like whatever insects are up there. I don't know. What's the point if there's no mental stimulation? So anyway, we got this business going on here. So from this I can say that x is equal to, because remember this is the augmented matrix, x is equal to 9/13 minus 6/13 z, y is equal to negative 5/13 minus 1/13 z, with z being our free variable, z equals z. Now we can let the parameter be z. GeoGebra will understand that just fine. I mean, in fact, we've let the parameter be z before. We just called it x3. So there's no reason why we have to change that up. So I would say x, y, z is going to be 9/13 negative 5/13 and 0 plus z multiplied by negative 6/13 negative 1/13 and 1. So this is a parametric model. All right. So again, we're using z instead of x3, but this should look very familiar. If I didn't have the rightmost column and I wanted to make it a homogeneous system, I would just get this component. Sorry, this component. But I have the particular solution, so I'm good to go. So I can put this all in GeoGebra, or I could sketch it out if I wanted to torture myself. But bottom line is now I have the equation of a line. But again, thinking back to the first unit, we always had an equation of a line. We just didn't know what we were looking at. All right, so now with a little context behind it, with a little ability to visualize, hopefully it starts making a little bit more sense. All right, so if I wanted to let z be equal to 0, then I'd have a point. The vectors actually are, you got to kind of think of them as the pillars that are holding up the functions themselves. All right, so it's not like you have just points floating out in space. Those points are suspended by vectors. That's actually something I could show you really quickly. And that's pretty much where we're going to leave it for tonight, but let me just show you this one last thing, and then I'll let you off the hook. All right, so I'm going to put in this function. So let me clear out this stuff. Yeah, because tonight was a big class. There's a lot of stuff going on. So 9/13 minus 6/13 z. I mean, I'll use t because I already have t stored in there, but it doesn't matter what you plug in. Then we'll have negative 5/13 minus 1/13 t. And then the last one is just, well, I would just use a t there. And then it would, it would span, I don't need 2 t's, just one. Wait, maybe I do, oh no, I do need the 2 t's because one of them is my z. And so that's what I have. I'm just letting z be some other variable so I can pop it into GeoGebra. All right. So now what I want to do is just draw a few vectors. I'm just going to plot a few vectors here. One of them would be what you would get if I replaced the t with a 0, for example. So I get this coordinate. So I'm going to plot the vector. So vector A. So let me get some of these labels off. These little tick marks can be kind of distracting. All right, but you could see that this new vector is pointing to a point on the line itself. All right, so then I'll do something like b of 1. So I have a new vector. So vector b. All right, then maybe I'll do b of 1.5. I could pretty much do anything because GeoGebra is doing the work for me. So vector c, vector. All right, then maybe I'll do b of -3, vector d. All right, so it's easier to see if I pull it out, but you can definitely see that that would follow the path. And then maybe one more for good luck, b of 6. Too big. B of 4.5. Still too big. I think it'll be fine. Yeah, that's good. Vector E. All right, so we have all those vectors that basically act like really struts or pillars that are holding up the line. All right, and that's the same thing with anything that's defined parametrically. Anything that's defined based off of vectors, vector value functions or what they're known as. And so what they're doing in all cases is, like, again, it's not like this is a line that's just floating out there in space. What it is, it's a line that's being lifted from the XY plane, right? Based off these vectors. So if I had a line on this XY plane, and then I had a bunch of people at different locations just propping up that line, right? So I hold it up over here, maybe somebody on this side holds it up over here, and then you have a couple of people supporting it like a piece of string or something, or a flimsy piece of wood, where it won't hold its shape unless you have lots of individuals holding it up at different points. Then you would have this linear function, but it's being suspended from the ground up. So not like it's being held from the ceiling, but it's actually being pushed up from the ground level. That act of pushing it up to hold its place, those are the vectors that form the vector valued function, right? And they form the basis of this kind of system. So you're talking about a system that is function related, but also has the characteristics of both, right? So characteristics of linear systems and all the stuff that we've learned about with that, with row reductions and all that good stuff, but also has characteristics of functions themselves, domain, range, derivatives, antiderivatives, and things like that. So we're getting to the part of the course where we're going to start marrying the two ideas together and see what happens. All right? So it's a pretty fascinating component of the course. So the idea that we're going to be able to take matrices and incorporate the calculus to it, that's pretty exciting stuff. All right, so that's where I'm going to leave it for tonight. And so if you have any questions, stick around. If you came in late, definitely check on me before you go. Otherwise, have a wonderful evening. I'll see you on whatever the next day is.
So you already did the attendance in the beginning of class?
Yeah.
Oh, okay.
So you're good.
Thank you.
Because you were early today.
All right.
Yeah, I remember that.
All right.
All right, man.
Just keep it as a habit, right?
Yeah, exactly. Just keep doing that. It'll be fine. I'll get you for attendance too. Josh is down again. Okay, well, there goes that.
Attendance, please.
Ah, yes. No problem.
Like him, I don't know.
Let's see. I think you were like right in the beginning, right? Yeah, you were here. I remember because you came in, then went back out, and then came back in. Yeah, you were fine. It's really just. And that's the one that's late all the time. Let's see. Everyone else is here. Yeah. Okay. So we're all.
I was here at the beginning, I just didn't hear you call.
Yeah. I just did the look around. It generally works this way. Pretty clean attendance wise, except, you know, head cold.
Migraine.
I take my medicine every single morning for that.
Which next?
Topiramate.
I used to have them like 4 times a week when I was growing up, and I got much better as I got older. Every now and then, if I wanted to start touching out of nowhere.
Yeah.
It's infrequently enough, fortunately, that I don't need